The last video, we spoke a lot about energy. We talked about its various forms, its transformation in terms of from, let's say, chemical energy in a battery to light energy in a torch. We also gave a lot of examples from mechanical systems, like a ball rolling down the hill, an object moving up a hill, the amount of work done to take it up, the amount of energy recovered, the potential energy, the kinetic energy, and so on. Let's today concentrate on a specific form of energy called light energy. Most of us have no difficulty in visualizing light because the most ardent way to visualize light is morning and night. When you wake up in the morning, the sun is out there. It's bright because the sun is kind of giving out light energy and illuminating everything that you see. At the same time, when sun sets, everything becomes dark. Same way, when it is bright, you see a lot of white color. The sky is really white. And then when it is evening and it is dark, the sky is black. In some sense, in the most rudimentary way, color, which is typically what we call as black and white, although they're not colors, white is the presence of full capacity of light, whereas dark is really the absence of light. So in some sense, when we talk about color, it really is white color, which is technically not a color, but is a combination of everything that you see as color put together. You probably have done experiments in lower classes of coloring a disc with 5 or 6 colors and then rotating it very fast, and suddenly all you see is white. That's because white is made out of these various components of different colors. In terms of energy, light is actually electromagnetic wave which carries energy, as is something like a radio frequency wave, which is where the cell phone transmission works. Cell phone energy is actually transmitted in terms of radio frequency waves. Light is a special class of that electromagnetic wave which transfers energy in terms of alternating electric and magnetic fields. The wave has a specific character called wavelength, and each wavelength is actually a very specific color. When you have a range of wavelengths sitting together and mixed up very well, you get what is called white light, which is composed of typically what we call the violet, indigo, blue, green, yellow, orange, and red, which are the spectra of colors within the white light. So black is the absence of light, white light is the full presence of light having its full components. To look at light, let's look at what happens when you walk into a dark room. You obviously can not see anything in a dark room because there is no light to see it with. And therefore, light is also a perception of what our eyes can see. But when you walk into a dark room, you turn on the light and suddenly everything illuminates up. If you have a tube light like I have in front of me on the top, it's white in color. But it does not make the entire room white. For example, the background wall that you see is a bluish greenish color. It's a mix of blue and green. So white light is sifting through this room and illuminating the entire room, but you are seeing different colors. For example, you see the painting above, it has a very different set of colors on it. So the light energy that's coming from the tube light is white in color because it contains all components of the light that we talked about in terms of the wavelengths from violet, indigo to all the way to red. But when it falls on the wall, the light bounces back from the wall, which is what you can see through the lens in the camera. So in some sense, the light is altered depending on what that surface is. First of all, in terms of color, what was a white color from the tube light hit the wall and actually came out as green color. So the first thing that we learn is about reflection. Light goes, hits a surface and gets bounced off. That process is called reflection. You will now ask, why is this different from if I had a mirror at the back? Right now it's not like you see the back of my head on the wall is just blue in color. So then reflections again are of two types. One where the surface is extremely plane and light comes and bounces off exactly in the same direction that it came from, just reversed in terms of angle, which is what happens in front of a mirror. All the quality of light, the way it came, hits the mirror and gets reflected in exactly the same way. But there's also a diffuse reflection where you really don't see the component. For example, if I had a mirror at the back, you would have seen the tube light in the mirror, but you don't see it because the kind of quality of reflection that you see from this surface, because it is not very smooth, is kind of the light coming in, hitting the wall, but going away in all directions. That's why, although the tube light is at one place in the room, by hitting the walls around, it's able to illuminate the rest of the room. In terms of color, because this paint has a certain pigment, which has the property of being able to reflect only that color, you see the color as the bluish green. And what happens to the rest of the white light? The other components of the light are absorbed by the pigments which are there in the paint. So therefore, when light forms, there are only three things that can happen. It can get reflected, it can get transmitted, or it can get absorbed. The entire air in the room is simply transmitting the light through, and that's why you don't see the air, because it's simply transmitting everything that goes through. Every other surface that's there in the room is reflecting the light back, and therefore you're able to see that light because it's hitting the wall and it's coming into my eyes, so I'm able to see that there is an object. But it's also partly absorbing the light and therefore only reflecting some parts, and therefore that is green, something else is orange, because it's only reflecting orange and absorbing everything else. That's how colors, reflection kind of alters the colors. However, if it's a mirror, it stays true to all the way the light comes in, it kind of sends it back in the same direction. That's why that's called regular reflection. Whereas when light gets reflected, another word that's normally used is scattered out of surfaces which are not very, very plain and smooth like a sheet of glass, you only get a perception of the light getting reflected, but you don't really see anything in it. And that's called either specular or diffuse reflection. So what can light do? Light can reflect, light can be transmitted, or it can be absorbed. And I kind of shortly told you everything that happens. With a plane surface like a mirror, another property holds. If a light comes and hits at a certain angle onto the surface of the mirror, it kind of bounces back exactly at the same angle but on the opposite side. And that's called the first law of reflection, where it said the angle with which it came in is the angle at which it left, and that's called angle of incidence is equal to angle of reflection. So mirror is a beautiful way of kind of deflecting light in exactly the angle that we want. I don't know if you've seen a periscope, but a submarine in the olden days, of course, used something called a periscope because it was under the ground. It just pulls out a tube, and light is kind of just bent so nicely through a periscope that sitting underwater, you're able to see what is above water simply with the use of two mirrors. You probably have a picture that you can see of what a periscope does. That's because the mirror nicely reflects the light in a particular angle, and because we place it at 45 degree, it perfectly reflects it by a 90 degree. It bends the light by 90 degrees. So you're able to kind of, with two bends, kind of take up the height at which you see versus the height of the object that you are seeing. So that's all about reflection. The laws of reflection necessarily don't change if the surface of the mirror was not plane. It was very reflecting and smooth, but what if you curved it? You realize and begin to see artifacts. I don't know if you've gone to the hall of mirrors that are there like museums, where you go and stand in front of the mirror and you look very different. You either look fat, you look thin, you look funny. It's simply because the surface is no more plane. So at each point in the surface, while angle of incidence is equal to angle of reflection, with respect to your eyes, they're just kind of all over the place, and you see a perception of the image being very distorted or being changed from what it is original. That's what you do in front of a convex or a concave mirror, or of course irregularly shaped mirror, but the laws of reflection remains the same. If you've seen a car rear view mirror, you'll kind of see objects are closer than you think. That's because you use a convex mirror so that the driver has a larger field of view than against if we had placed a plane mirror. So it enhances the field of view, which means he can see a lot more behind him in terms of what the normal eye would see. But of course, it then distorts the sense of distance, and that's why you have those wordings there that you need to be careful, because it is a convex mirror. So that's all about reflection. We also talked about transmission, right? So I said the tube light sitting there is simply getting filtered through the air, and it doesn't look like the air is doing anything to it. But let me give you another example. Just like the air is transparent and is transmitting, so is a glass of water. But if you were to place a pencil inside a glass of water and look at it from the side, the pencil kind of gets bent or looks bent between how it was in air and how it was in water. That property of light that kind of behaves differently in differently transparent materials like air and water is called refraction. That's because in air you don't see that artifact, because the speed of light in air and in vacuum are similar. But then the speed of light is altered when it has to pass through a denser medium, like let's say water. Water is more dense than air, and we did talk about density, and this is of course optical density, but does come from material density that we spoke about in the matter chapter many videos ago. So when it goes to a denser material, the speed of light slows down. And in some sense, what you observe though, because you can't kind of see the speed coming down, what you observe, it looks like it is bent. The way to visualize it, if you were seeing an army of soldiers walking towards you and suddenly you had drawn a line on the floor and they were working perfectly towards you, when they see the line on the floor and let's suppose they slow down and they begin to walk towards you at a slower pace, you will not make out any difference. So you will not see any bending of the line of soldiers that's coming to you. Imagine though that the line was in front of you, but the soldiers were coming at an angle. Now as those soldiers are walking in, one of the soldiers on let's say the left side is going to see the line immediately, first. And he stops walking a little bit slower. The second guy next to him is going to come to that line a little bit later, and he is going to start walking a little bit slower a little later. And therefore, if they were to maintain that sense of line, you would see that the only way they can maintain it is they kind of adjusted the angle at which they were coming to you. And that's exactly what refraction is about. It's about saying that light enters not at a normal direction, but comes at an angle from a rarer to a denser medium. It kinds of bends in. Similarly, when it is leaving from a denser medium to a rarer medium, it kind of bends out. That property of bending of light, when it has to traverse an interface between a rarer and denser medium, is called refraction. The last property of light, which we will talk about, is called dispersion. Now, this is a very, very beautiful articulation that you see in a rainbow. We also said all this bending is true when you're looking at white light. But if you, in a special circumstance, the dispersion, the angle by which it bends, is actually dependent on the light itself. We told you that white light is a combination really of multiple colors of light, starting from violet, indigo, blue, green, yellow, orange, red. This is the visible part of the light. That light, if it were to bend differently, each light were to bend differently away, you would see that they kind of split up. What looked like a bunch of people of the same color coming together, if they suddenly bent out a little bit more than different, and each of them kind of broke up into their components, that's dispersion. And you see dispersion beautifully in a rainbow. That's because white light from the sun is refracted through droplets of water that are suspended in the air post a rain. And because that refraction happens differently for different components of the wavelength of light, the white light then splits up to its original components, which are violet, indigo, blue, green, yellow, orange, red, and kind of sprays itself beautifully on the other end of the sky, showing a band of colors that came in from a single beam of white light. And that, dear friends, is a rainbow, and spectacular. Of course, this sort of romance that goes away if you start thinking about the physics of dispersion while you're watching a beautiful rainbow. But that's exactly the reason you need to understand that's not necessarily something that happens by nature alone. It happens because of the laws of physics operating together with the laws of nature, and gives you a resplendent color from the white light from the sun. So today we spoke really about energy, light as a form of energy, and principally three big things that light does, which is reflection, refraction, and dispersion. Reflection, where light just goes in, kind of bounces off. It can bounce off two ways, either in a specular way or in a regular way, or a diffuse way, as it is called from a specular point of view. Or it can bend, which is refraction, and because it bends and can bend differently for different components of the light, it can disperse into its various colors. So with that, I think I will stop here, taking you through the various aspects of light energy. There's a lot of it in the books in terms of geometry of saying if a light were to come in a certain angle, using the angle of incidence equal to angle of reflection, depending on what kind of a mirror it is, with a plane mirror or a curved mirror, and a curved mirror can be concave or convex. You can kind of draw out those geometric diagrams, or ray diagrams as they are called, to figure out what's happening. But fundamentally, that's what is happening in what you see in light playing around, which is a form of energy, playing around with the media that it encounters, which can be air, which can be surfaces, which are either smooth or are kind of, rough, as well as can be perfectly reflecting, and of course some of them can absorb, and that's why you see different colors. So I hope you appreciate light, and the field is really called optics as a subject, but also as a chapter in this case, and see how light energy is kind of bouncing around the room to take the energy of what the tube light was fed with, which is electrical energy, to convert it into light energy, to give you all the perception of what really light looks like. Thank you, and look forward to speaking to you again on another topic and another form of energy. This is me signing off today. Bye.